where t runs from 0 to 1. And the value of c of t is shown in the transverse direction. And what is the requirement on the c of t process? Well, that whenever 2 points in my Brownian excursion correspond to the same point on the CRT, but then their value of the snake should be identical. So that's why we see here the nice wiggling behavior in the transverse direction. Or to put differently, if we have a CRT, then what is the Brownian snake? Well, it's a Brownian motion that lives on top of the CRT. So it's a Brownian motion indexed by the points of the CRT. But yet differently, it's a centered Gaussian process that is specified by its variance. The values between 2 points S and T on their CRT should exactly be given by the distance along the CRT. Okay, so this is the Brownian snake, and it is by now well known that if you have a Brownian snake, you can construct a continuous metric space out of this, essentially by taking the CRT and identifying 2 different points on the CRT precisely when they have the same value for this label process C. And if I follow the contour between these 2 points, that the labels are strictly larger in between. This is an informal description on what the Brownian sphere is. So let me not give the very precise definition of Brownian sphere here, because I think that Jean-François Legal this afternoon will actually provide more details. Let me just say it's a random continuous metric space that almost surely has the topology of the sphere and a Hausdorff dimension that is not equal to 2 but equal to 4. It has very many interesting properties. What I'd like to emphasize is that it has been proven for many types of planar maps, including p-angulations, uniform maps, simple triangulations, quadrangulations, and many more families, that they possess a Gromov-Hausdorff limit in terms of this Brownian sphere. After every time renormalizing distances by the 4th root of the size of the map. So I can also mention that the Brownian sphere can be recovered from Liouville quantum gravity at a particular value of the coupling. But the main message here is that with some novelty in the theorem that I just described, in the sense that we reproduce the Brownian sphere limit, now starting not from a discrete model, but from a continuous model, which are these random hyperbolic surfaces. Okay, but of course we're going to mimic what has been done for random planar maps. And all these convergences for random planar maps to the Brownian sphere relied very heavily on having these trees that also nicely encode distances to a particular distinguished point in the surface. So the first real question I have to answer is, what are the analog trees for these hyperbolic surfaces? So let me show you where these trees are. So here I have a hyperbolic surface with cusps. And what I've done is I have taken a random such surface, but with 2 distinguished cusps. That's why I put a double prime in my moduli space. So one of them that I'll indicate by a star, and we'll usually call the origin, and another one indicated by this triangle, which I'll call the root cusp. And what we're now going to do is we're going to look at the cut locus of the origin. So what is the cut locus? It is the collection of points in the surface that have more than one shortest geodesic running into the origin. So how can we see where these points are going to be? Well, if we look at this horocyclic neighborhood, then all of these points here, they'll just have a unique geodesic running into the origin. But if I grow the size of this horocyclic neighborhood, and at some point it will wrap around some of these other cusps, and then I'll find some points here that lie on a geodesic segment that have exactly two shortest geodesics. So one running on this side and another one running on the other side of the surface. So if I keep growing this, I'll find all points that have more than one shortest geodesic. And actually these points generically group up into a tree structure where all the edges of the tree are hyperbolic geodesics themselves, and they either end at one of the cusps that is not the origin, or they end on a vertex of degree 3. So which are the points in the surface that have exactly 3 shortest geodesics running to the origin. So generically, this cut locus is really a tree, and it's a rooted, because we can root it on the root cusp, plain binary tree with the number of leaves equal to the number of cusps minus 1. Now what we can do is we can look at the angles at the vertices of this tree. And what we'll see in a minute is that if we look at 2 neighboring vertices in the tree, look at the angles opposite of the connecting edge, then they will always have a sum that is larger than pi. And the claim is that if we know this tree, together with all the angles on the vertices of that tree, that it completely encodes the geometry of the surface. So let me quote this as a theorem. So it's not entirely true that it's always a plain binary tree, because it can happen for some special hyperbolic surfaces that we have vertices of higher degree. Or it can also happen that we have more than one geodesic running into the cusp. But all these singular configurations together have 0 Well-Petersen measure. They have probability 0 of occurring. So if we remove all those singular configurations, we're left with an open subset of the moduli space of full Well-Petersen measure. This open subset is really in bijection with a disjoint union, where the union is over all kind of combinatorial classes of binary trees, together with a specification of the angles that the tree can have. And the only conditions are that these angles, so here I just record 2 of the angles around each of the vertex, that the angles should all be between 0 and pi, and they should satisfy this condition whenever you have 2 neighboring vertices. So this is the tree bijection that we're going to use. Now, this would not be useful, this tree bijection, if the Well-Petersen measure would be complicated in terms of the tree, but actually it's very simple, because the Well-Petersen measure is just mapped to the Lebesgue measure on these angles, up to a power of 2. So let me give you some intuition for why this theorem holds. And the idea is that when we have the cut locus, we can look at a dual triangulation of the surface. In what sense? Well, for every edge of the tree, so for every segment here in the cut locus, we can look at the dual geodesic. So that is the geodesic that is dual, for instance, to this edge of the cut locus, is the geodesic that starts at the origin, intersects this edge, and returns to the origin. So there will be a unique geodesic within this homotopy class. And this is true for all the segments in the tree. And what it does is it produces a triangulation. So for instance, around dual to this red vertex, we have 3 geodesics that form the sides of an ideal triangle. in the hyperbolic surface. Now, we can also look at the neighborhoods of a cusp. We have to draw another shortest geodesic from the cusp to the origin, open up our surface along that geodesic, and then we see that we also have a triangle sitting there that is glued along two of its sides to produce a cusp region. So to summarize, if we have this plain binary tree, for every vertex in the tree, we have a dual ideal triangle, and they're glued to each other, well, according to the neighborhood relations of this tree. So given our binary tree, how can we reconstruct our surface? Well, you have to tell the triangles how to glue to each other. And one way to do this is to say that, well, we still have parts of this cut locus within every tree, and the position of where the red edges meet the sides of the triangle tell us how to glue these triangles together. Because this is an ideal triangle. So this is a triangle, a hyperbolic triangle that has an infinite side length. So without specifying how to glue, there is like a one parameter degree of freedom of how to glue these triangles together. But if we specify where the cut locus meets the sides of each triangle, then we can uniquely reconstruct the surface. And now the claim is that specifying where these red edges meet the sides of the triangle is equivalent to specifying the angles at the vertices of this tree. So here I've drawn one of the ideal triangles in the upper half plane. So I can always draw it in such a way that two of its vertices are at 0 and 1. And the third vertex is up at infinity. And then for every position of the red vertex, one can always find geodesics that meet the boundary perpendicularly. So in order to specify where the red edges intersect the sides is equivalent to specifying the position of the red vertex of the cut locus within this triangle. And I said that this was determined by the angles alpha and beta. An easy way to see this is that if I draw these line segments to 0 and 1, then I can easily read off those same angles in the angles that these segments make with the real axis. So this immediately tells us that our angles alpha 1 and beta 1 for this particular triangle have to be between 0 and pi for this to be a well-defined angle. And also that they have to add up to something that is larger than pi, because otherwise these segments would not intersect each other and not specify a red vertex in the upper half plane. Now there is one detail here that I have to discuss, and that is that it's not necessary that this vertex is actually located inside of the ideal triangle to which it's dual. It can also happen that it's outside of this triangle. And this is what slightly complicates the story. And why is that? Well, if I then look at how two neighboring triangles are glued to each other, what I have to do is I have to take this picture and glue it to its neighboring triangle. But I have to avoid that the center of this triangle clashes with the center of the other triangle. Because if this vertex here would be to the right of this vertex there, then this edge would simply not exist. And we have to ensure that it does exist. So what is the condition? Well, simply by drawing these arcs, we can read off what the condition is. This angle can also be seen down here. This angle can be seen here. So the condition that this edge exists is that alpha 1 plus beta 2 here exceeds pi, such that we have a positive angle between these two line segments. And therefore, this edge really existed that is dual to this triangle side here. Okay, so that explains why the angles are sufficient to describe this surface. What we can then look at is whether the angles also naturally encode distances in these surfaces. Because this is what is necessary in order to study distances in the full surface on the level of the trees. And this is really the fact. So if we look at the hyperbolic distances from edges of this cut locus to the origin, or say to the horocycle around the origin. So in this upper half plane, they correspond to distances between these red geodesics and the 3 copies of the horocycle that you see there. Then they're directly related to these angles through a hyperbolic version of the sine law. So particular differences in distances of the 3 different red edges here to the origin horocycle are specified by the angles around this vertex. And finally, I have to explain to you why this Peterson measure is so simple in terms of the angles. For this, you can take an explicit formula by Penner for the Peterson measure for any triangulation of a surface in terms of these types of distances. And you can plug in the sine law, and with some magic, it turns out that this is simply the Lebesgue measure on the angles. Okay. So that was the main projection. What we now want to do is to prove, just like in the planar map case, that these trees scale towards something that is encoded by a Brownian snake. Because the Brownian snake is the thing out of which the Brownian sphere is constructed. So what we do is we're going to sample a random surface with 2 marked cusps. And we just said that that is the same as sampling a random plane rooted binary tree, Tn, with a probability that is proportional to the Lebesgue measure on this polytope of angles that it allows, that satisfy 2 constraints that I showed before. And then on top of this random binary tree, we sample Lebesgue uniformly from this set of angles, random angles, that we put on the tree. Next, what we do is we take our tree and we're going to label it by the distances to the origin. And we've just seen that using the angles, we can actually determine these distances. So we label every edge of the tree by the distance to its horocycle. But we shift all distances such that we have label 0 on the edge that is incident to the root. And what is nice here is that if we then look at the labels that sit on the edges that are incident to the leaves of the tree, they correspond precisely to the differences in distances between the corresponding cusps compared to the root cusp to the origin cusp. So if we understand these labels on the tree, if we understand their scaling limit, we know something about distances between horocycles, which is what we're after. So what we then do is we take our tree together with the labels and encode them in processes, just like for the planar maps. So we can look at the contour process. So we follow the contour of the tree and we record the height of the vertices within this tree, starting from the root. This is the contour process. We can also look at the label process, which is a piecewise constant function that just records the label of every edge when following the contour. And finally, we look at the leaf counting process, which just records the number of leaves that we've seen so far when we follow the contour. So this is the R of n. And the main kind of technical result that we need to prove the convergence to the Brownian sphere is that these three processes combined after suitable normalization by powers of n converges to the Brownian snake. And that the leaf counting process converges just to a deterministic linearly increasing function, which tells us that the leaves are really deterministically uniformly distributed along the contour of this tree in the limit. Okay, so let me give you some hints to why this particular convergence holds. And from the planar maps, we're really used to proving this, or other people are used to proving this convergence. When we can find some nice trees, some nice BNMA Galton-Watson trees in the representation that we have. So the first thing we should do is make the trees of random size. In particular, we're going to make them critical. So the number of punctures in our surface will now be a random variable with the probability of having a certain number of punctures proportional to some critical constant xc to the power of the number of punctures. This turns the trees also into critical trees. But unfortunately, these trees are not of the form of BNMA Galton-Watson trees. In a sense, they're continuous type trees. So we could say that to every vertex in the tree, we could assign a type, which is really a real number between 0 and pi. And the offspring distribution of these trees depends on the type. Let me not go into detail how these types describe the offspring distribution. But the point is that we do not have good invariance principles for these random trees that have a continuous family of types of vertices. So the big question is, can we find within these continuous type trees some single type regular Galton-Watson trees? And the answer is yes. So how can one do this? Well, we notice that these trees are dual to the triangulation of the surface, which is graphically represented here. But there are some places where we can naturally dissect the surface. Namely, we can dissect the surface at the dual geodesics that intersect their respective edges in the red tree. This leads to a decomposition of our triangulation into smaller building blocks that we call the blobs. And what we can then do is look at the tree that encodes the connectivity of the blobs. And this tree is a standard Galton-Watson tree with an explicitly known offspring distribution, P of k, with a slight modification at the root. Okay, and we have a well-described procedure of how to rebuild our original tree and surface starting from this black tree. And what we now would like to do is take our black tree that encodes the connectivity of the blobs and study the labels, so the distances in our surface on this black tree. And if we do this, then what we find is that the increments on our black tree, the increments of the label, actually have very nice properties. So first of all, they're independent from one vertex to the other. And second of all, they are locally centered, meaning that every increment, say the increment of the second child of this black vertex, has 0 expectation value and some good moments. And this sets the story a bit apart from many planar map models, where we do not have this local centralized behavior. And really, this is a bit of a difference of the tree bijection we have here compared to planar maps, in the sense that the trees completely respect the symmetries of the surface. Well, for planar maps, you often have to break the symmetry. For instance, in the Schaefer projection that I've shown before, the menu by which I constructed the tree was actually changing or breaking the mirror symmetry that might be present in the surface. But here we have exact central increments. And that means, okay, so and this is really due to a mirror symmetry we have in the surface, that we immediately can apply the invariance principle of Marque and Bernion to tell us that the contour process of this black tree, together with the labels on this tree, converges to a Brownian snake when the number of black vertices increases to infinity. Okay, so to actually prove our final convergence of the contour and label process to the Brownian snake, we have to do some reconditioning, reintroduce the red vertices into the tree. But I'm not going to comment on this. Now, as soon as we know that distances and the contour process of our final kind of encoding tree converges to the Brownian snake, the main extra ingredient one needs to prove convergence to the Brownian sphere is a bound on distances between arbitrary pairs of horocycles. So here again, I'll have to skip some details, but a natural way to address this problem is to open up our surface along the cut locus. So that turns our surface into a hyperbolic polygon that has a single puncture in it, which we can nicely represent in the upper half hyperbolic plane. And distances to the origin are nicely encoded in kind of the vertical distances in this upper half plane. And then we can actually find some bounds on distances between cusps by constructing some nice paths within this, this hyperbolic polygon. And this tells us that the distance between two arbitrary horocycles Ci and Cj can be bounded in terms of the distances to the origin horocycle minus a minimum over the labels along this, this tree, with a slight error, so error that is really small compared to typical distances. So combining these ingredients together with rerouting invariance of the model that we started with, this origin cusp that we chose, it was just a uniform cusp. We can apply Legall's rerouting trick, and by this find that the hyperbolic distances parametrized by the contour of our tree actually converge to the Brownian distance function on the Brownian map. And this then implies the Gromov-Hausdorff convergence of this set. Okay, let me skip this. Yeah, I think I'm out of time. So let me stop here. I hope there was something to Jean's liking in the Brownian spheres, and perhaps the hyperbolic surfaces will be a nice new topic to investigate for some of you in the audience. Thank you.
Thank you very much. So thanks again for a very nice talk. So do we have questions? Yes.
Well, thank you, Timothy, for this very nice lecture. And I had a naive question. So in your results, it seems that these angles, alpha I and beta I, play a major role. And I was wondering whether one could define something similar in the continuous limit. I mean, you can make sense of the cut locus also in the continuous limit, and you can also look at the branching point in the cut locus as you had in your tree. but there is nothing similar to these angles, I suppose.
No, so one would expect that all these angles really disappear in the scaling limit. So everything that we find in the scaling limit is just the Brownian snake. Whether there is some way to find something in addition to the Brownian snake by maybe some subleading scaling behavior, I really have no idea.
Okay, are there other questions? I think we have one in the chat.
Yes, so thank you, Timothy, for this very nice talk. I had a naive question regarding your parameterization with this T. So I was wondering, what is it, this T parameter? I missed the definition.
You mean this parameter T here?
Yes, yes.
Okay, right. So we start with the discrete processes, which just take time 1 to traverse each edge in the contour. And then simply we rescale the time uniformly such that it ends at time 1. So it's just a combinatorial parameter that parameterizes the contour.
In the end, I understand that it is somewhat irrelevant because in the end you have it with your leaf counting process. Give you more canonical definition, if you understand.
Exactly, yes. So the only reason to have the parameter T here is because then we can apply these invariance principles easily. But what we're really interested in is the parameterizing the contour according to the leaves that we've seen. And so in the scaling limit, it does not matter.
Okay, thank you.
Are there other questions? Yes, we have a couple.
Would you expect your result to hold for other compact surfaces, torus or arbitrary genus? Maybe it's a question also for Gregory and Jeremy.
Well, one would certainly expect that if you take the Peterson sampled genus G surface with n punctures and perform the same scaling, that one would get a convergence to the Brownian genus G surface. But okay, again, proving such a convergence will be exactly or even more difficult than proving this convergence for planar maps. So I'm certain there are some people in the audience that can much better comment on this. I think is Jeremy Bettinelli there or Gregory?
So, sorry, I was discussing with what was the question? I'm not supposed to be asked a question. No.
It was not a question. I just said that you would be in a better position to answer.
Okay, so I think we have another question.
Hi, it's probably related. So can you, for instance, deduce easily convergence to a Brownian disk instead of a Brownian sphere? And yeah, I don't know if you answered Jean's question. Like, how about stable surfaces? Like, what would be the analogous?
Yes, so this is a good question. So to go to surfaces that actually have some boundary components or stable surfaces that have holes in them, one certainly has to go beyond hyperbolic surfaces with punctures, because we need some boundaries there. And naturally, one would look at hyperbolic surfaces with geodesic boundary components, so of which the Wald-Peterson volumes are very nicely computed by Mirzakhani. And indeed, for genus 0, it seems that there is a nice generalization of this bijection for such boundary components present in the surfaces as well. So if you like, the bijection that I show here is the natural hyperbolic analog of Schaeffer's bijection. But there is also a nice analog of the Bucce di Francesco di Dare bijection for maps with arbitrarily size faces, corresponding now to hyperbolic surfaces with arbitrary length boundary components. So one should look at the level of those trees and study the scaling limits of those trees to understand the types of surfaces that you're asking about. But this has certainly not been done yet.
Okay, do we have maybe one last question? There in the chat. Okay, maybe I can ask a quick question. So you mentioned the fact that your result is a kind of first situation where you get the Brownian sphere from a continuum model. Is there a way to bridge the gap between random maps? I mean, between maps, planar maps, and hyperbolic your model?
Yeah, so that is a very good question, and I think it's still largely open. So I have a slightly different line of work where I study a relation between certain maps with an irreducibility constraint and hyperbolic surfaces. But that is not the connection between maps and surfaces that naturally explains this tree bijection. So on the level of this particular tree bijection, I really do not know what a direct connection with planar maps would be. But one should certainly keep an eye open for such a connection.
Thank you very much. So I suggest we thank Timothy again.